Okay, students, welcome back. We're ready to start thinking about how we're going to use some kind of inferential statistic to reach some kind of conclusion about what our data are telling us about the system. What they're telling us about how one group of students might be taller than the other group of students, as was our example in the previous lecture. Or might be telling us about which solar panel is able to produce more power, or which wind turbine was in a location that it had more wind available to it, and so on. All of this is going to require that we write hypotheses that then we're going to be testing. And this actually comes to us from the scientific method. Now, the scientific method is the kind of thing that's been beat into your head so many times in your education, and every textbook has a slightly different listing of the steps of the scientific method and so on. And you have seen this so many times. You've seen this really your whole life. And the reason why I know that is because I have two little boys, and they are nuts about every PBS cartoon out there. And every PBS cartoon out there nowadays talks about the scientific method. Right here, we're watching Dinosaur Train. And Dinosaur Train has three little dinosaurs and their mom go around on the dinosaur train to meet a time-traveling train to visit dinosaurs of different periods and learn about them. And Buddy, the T-Rex, who inexplicably isn't just eating the other dinosaurs, but whatever, Buddy the T-Rex always has a hypothesis he wants to come up with. I mean, he's looking at just one little part of the scientific method here. Broadly, he's trying to answer questions about the world around him. Now, on Dinosaur Train, they're not necessarily doing any background research before they start a project, but clearly any kind of research project you were doing, you'd first want to, say, read the available scientific papers and make sure that you were doing something that hadn't been done before and so on, where you could just look the answer up, which would be a whole lot easier than doing the work. Then Buddy constructs a hypothesis, and that's his forte. Buddy always says, I have a hypothesis. Man, I've seen these cartoons a zillion times with my boys. Then, in the scientific method, you find a way to test your hypothesis, which gives you a way to analyze your data and draw some kind of conclusion. And then there's the whole business of communicating your results, which on Dinosaur Train is like a party or something like that. But in this real world of science or engineering or something like that, it would be things like journal articles or presentations at conferences or posters or something like that. But this business of constructing a hypothesis is a not entirely simple thing. I mean, almost every time that Buddy wants to, I have a hypothesis, someone asks, some other dinosaur comes along, well, what is a hypothesis? And Buddy or Buddy's mom, again, who's inexplicably not a T-Rex, but we don't worry about that, on the show comes along and says, oh, a hypothesis is an idea that can be tested. Now, what does that actually mean in Buddy's little world? In Buddy's world, that means something like, he has a hypothesis that these blue dinosaurs have long necks so that they can eat the leaves from the top of the trees. Okay, when you're a 5-year-old watching Dinosaur Train, that's a great hypothesis. That's an idea we can test if we're on Dinosaur Train. So Buddy asks the big blue dinosaurs with the long necks to reach up to the trees and taste those tasty leaves up on top. And so Buddy tests his hypothesis, and the dinosaurs say, this is delicious, this is what we do. We eat the trees leaves. Or if it's a different species of dinosaur, sometimes those kinds of things don't work. I remember there's one episode of Dinosaur Train where they try to eat the leaves at the top of the tree and they weren't delicious. Or I think one type of dinosaur his heart wasn't strong enough to pump blood up that high or something, and he fainted. And so Buddy's hypothesis was wrong. Okay, well, that is a type of science. In the sense that, like, they formulated a hypothesis and they tested it. But, I mean, this wasn't actually a very rigorous scientific test. I mean, just because the dinosaurs... Did Buddy's hypothesis fail when the dinosaur reached up there and tried to eat the leaves at the top of the tree, but the leaves at the top weren't tasty? No, I mean, maybe different trees would have tasted different, or maybe those leaves would have tasted good to a different dinosaur. Buddy's hypothesis was not being very rigorously tested here, but again, we're talking at a show aimed at, like, the 5-year-old crowd. So, this idea of constructing a hypothesis, whether we're talking you learned it on The Cat in the Hat, or you learned it on Sid the Science Kid, or whether you learned it on whatever, was going on, Miss Frizzle's, what's that, the Magic School Bus, maybe the age that you guys were, I don't know. they've been, from elementary school on and probably earlier, the world's been telling you about this idea that science is a way of solving these problems. And that's a good thing, because science as a method is one of the best things we've ever invented. Right? This whole process is how our world advances. And one of the key steps is how to construct a hypothesis. And we're going to be doing that now. We're going to be very rigorously performing what is called hypothesis testing as a way of trying to find out what kind of information we can infer based on observations, data. All right, so forgetting about Buddy, and yeah, that's his friend, the conductor, who's the guy who drives or conducts the dinosaur train there. If we forget about them for a moment there, we're gonna have a formal hypothesis testing here. Buddy doesn't formulate two hypotheses the way we're going to. In formal hypothesis testing, you'll always have two hypotheses for any given experiment you're running. The so-called null hypothesis and the alternative hypothesis. If Buddy were formulating a null hypothesis and a alternative hypothesis, there would be certain properties they have to fulfill, as we'll be seeing. They have to be exhaustive, they have to be mutually exclusive, all this kind of thing. That isn't the way Dinosaur Train works, okay? It's a show on when kids get up from nap. Let's actually talk about what we would do with this, how this null hypothesis would work. And I think it's best to just go back to the example that we had used in the previous lecture, where I was taking samples of students at Creighton and at UNO, take a sample of 10 students at each school, measure them, and compute their average. Now, that average is a statistic, it's not a parameter. What I'm really interested in is the mean of the heights of the students at Creighton and the mean of the heights of the students at UNO, but I don't have that information and there's really no way to get it. Okay, the mean is a real thing, but it doesn't, there's no way to actually observe it. So we have these statistics, like average, that we can work with. They're descriptive statistics, and we could look at them and we could say, it actually, if I did that sample many times, I would see that there's sort of a distribution to this. Sometimes my samples have relatively high averages, because, I happen to have several members of the basketball team on my sample. Sometimes my averages are low. Most of the time they're kind of under the hump of the distribution, etc. But no matter what, when I took my sample, I now had some average height of Creighton students, which we called Z-bar CU, and I had some average height of UNO students, which is Z-bar UNO. Z-bar, for each of those two schools, is an interesting statistic. It tells us something interesting about the properties of the students that we sampled, but it isn't actually telling us directly very much about the mean. Remember, we're going to use that symbol mu to mean the mean of whatever we're talking about here. Our first hypothesis, then, will be the null hypothesis, and the symbol we use for null hypothesis is H0. H0 will be our null hypothesis, and our null hypothesis will be, well, maybe there's no difference. Maybe the mean of the heights of Creighton students, mu, mean, is equal to the mean, mu, of heights of UNO students. That certainly is a possibility. Alright, now this is going to be one of our two hypotheses here. Now that might seem like the not so interesting one. That's okay, we're going to have a second hypothesis as well. But this idea of this null hypothesis, an older term for the same thing is that this would be the victim hypothesis. It's kind of an awkward terminology today, but it's kind of a useful thing. Think of this as being the hypothesis. Okay, it can be useful to think of this as being like what you're trying to disprove. Okay, you're a scientist, or you're an engineer. You're not actually, you're not approaching this with some agenda. But think of this as like, well, if my Creighton students and my UNO students have the same height, that's not intrinsically interesting compared to if one group is taller than the other. It's better to think of the null hypothesis as the situation in which there's no result, or you can't statistically prove what you were looking for. Okay? You can't reject the idea that the two groups are the same height. Okay, we could do all kinds of problems where we were writing a null hypothesis. You have two data sets and you want to correlate them. Your null hypothesis might be that they're not correlated, that R is equal to 0. Okay, Or if you're talking about the trend in a data set, you maybe had temperatures at your station with respect to time, and you wanted to see if there's a global warming trend in there. Your null hypothesis might be that the trend is equal to 0. Or if you were measuring the electrical load in Omaha, like what we saw in the Project 3. Remember there was a part where you did the trend in the electrical load in Omaha, or you looked at the annual cycle. Your null hypothesis might be that there's no annual cycle, things like that, okay? It's not that you're trying to disprove it, it's more like that's the no result, or that is, we can't statistically prove it. In contrast to the null hypothesis, we're going to have the alternative hypothesis. And the alternative hypothesis has a symbol HA. And in this case here, HA is going to be that the mean of the heights of students at Creighton is not equal to the mean of heights of students at UNO. Okay, and we're not even yet weighing, whether we think one is taller than the other. Okay, we're just saying they're not equal. Not saying that the averages aren't equal. The averages are probably not equal. You take any group of Creighton students and you take their average. You take any group of UNO students and take their average. It's not going to be equal. Okay? The question is, are their means equal? Are these two groups somehow different? Are Creighton students taller than UNO students? Now look here I put the two hypotheses kind of one above each other. I want you to notice that they have certain properties when you actually put the two hypotheses that we are going to be testing side by side like this. They have two properties that are important. These two hypotheses need to be exhaustive and mutually exclusive. By exhaustive, we mean that they contain all of the possibilities. No matter what the real relationship is between those two means, it's included in those two hypotheses. I mean, notice that I didn't make it so that my null hypothesis was that they were equal, and my alternative hypothesis is that they are equal on weekdays. Well, then there would also be the possibility about what if they weren't equal on what happens on weekends, right? For that matter, I didn't make it so that my alternative hypothesis is that Creighton students are taller than UNO students. Okay, that would be, if the null hypothesis was that they were equal and the alternative hypothesis was that one was taller than the other, what about the possibility that they are shorter than the other? So no matter what, you have to write the two hypotheses so that they are exhaustive. Okay, no matter what the result is, it has to fit into one of those two hypotheses. When Buddy the dinosaur was saying, "I have a hypothesis. Velociraptors have feathers because it keeps them warm." Okay? You could think of it as maybe he would have then a null hypothesis. Feathers don't keep the velociraptor warm, and a alternative hypothesis, the feathers do keep the velociraptor warm, and, well, that's kind of all the possibilities, right? There's no other possibility there. The other thing is your hypotheses need to be mutually exclusive. Mutually exclusive means that if one hypothesis is true, the other one has to be false. If you look back over here at our example where we're talking about the heights of Creighton and UNO students, it's not possible for both of these to be true. If the null hypothesis is true, the alternative hypothesis has to be false. There's no way you can be both equal to and not equal to when these two heights are being compared, when their means are being compared. They can't both be false either. Okay? Somehow or other, these two things are mutually exclusive. If one is true, the other is false. And if one is false, the other has to be true. Great. Okay. So we often hear this referred to as an experiment. Okay, especially in statistics, they would call this an experiment. So in the sciences, we would have called gathering all that data. Like setting up those solar cells or all that instrument, or gathering data from some website that contained the information that you were going to be analyzing. But either way, a statistician would call this an experiment then. All right, we're going to be testing these hypotheses eventually. Now, based on the data that we collected, okay, we measured 10 Creighton students, got their average height. Average, not mean. No, we don't have means in here. We have means here in these hypotheses, not averages. Okay, we collected 10 UNO students, and we took their measurements, and we figured out their average height. Average, not mean. We need mean, but we don't have the mean. So based on this data, we took these measurements. Can we now infer, Infer, based on evidence and reasoning. Can we infer that one of these things is true? Shockingly, the answer is no. We cannot prove that either of these things is true with our observations. And I don't mean the problem is just that we only took 10. We could have taken 100. We could have taken 1,000. That is not the problem. It is not possible to prove, as in to make it logically impossible that the other one is not the case. No matter what the data are showing, no matter if all 10 of the Creighton students were taller than any of the UNO students, it still doesn't prove that the mean Creighton student isn't. Still doesn't prove that the mean Creighton student is taller than the mean UNO student. There's nothing that could be in those observations that can prove that either of those statements is true. Rats. Okay, maybe it works the other way around. Is there anything in the data that could prove that, or that we could use to infer that one of these things is false? You know, like we could maybe say, based on our observations, we now know it's been logically proven that the null hypothesis is false, or the null hypothesis is true. Now, the alternative hypothesis is false. Strangely, too, the answer is no. Again, no matter what's in the data, no matter what the values are, it turns out you cannot prove, even if it turned out that everybody at UNO was short and everybody at UNO, you still can't prove it based on your samples. Statistics is weird. What good has any of this done for us then? It seems very frustrating. We've set all this up, and the basic thing we want, proving which of these statements is true and which one is false, we can't do. I feel like a very frustrated Buddy the Dinosaur, except for one thing. Buddy the Dinosaur has no emotional range whatsoever. You cannot ever find a picture of Buddy doing anything other than a smile. Trust me, I did a Google image search. The best I could do was him showing his teeth. Well, we can't prove, like logically prove, the way you like prove something in geometry or something like that. Well, one hypothesis is true and the other one is false. But with our data, if we can show you that the null hypothesis is really unlikely, that doesn't mean we've proved it isn't true, but we can prove that it's unlikely. That is, like it has a low probability of being true. We can reject the null hypothesis. I made that in a big fonty thing because it's going to be something that we're going to see over and over again. Reject the null hypothesis is a term in statistics. It means if we can say, look, that's not very with our observations, we can never prove that that is false. No matter what we have in our data, we cannot prove that the null hypothesis is false, but we can get some idea of how likely it is. We're going to use inferential statistics to determine how likely it is that that's true. And if it's not very likely to be true, we could reject it. Reject doesn't mean it's false. Reject means we don't believe that this is the case. Okay? Within some level of statistical significance, within some confidence level, we'll see all these terms coming back at us in future lectures, to some confidence level, we are rejecting the null hypothesis. We don't think it's true. We have not proven it's not true, but we don't think it's true. And if we reject the null hypothesis, by that business of them being exhaustive yet mutually exclusive, if you're rejecting the null hypothesis, you have to accept the alternative hypothesis. Again, that's a term that they use in statistics. Accept the alternative hypothesis. If you've rejected the null, there is no choice. The only thing that can happen is that you can accept the alternative hypothesis. So if you have shown that it is very unlikely that the means at Creighton and UNO are the same, then you can reject the null hypothesis. You can see why we kind of call it the victim hypothesis. It's the one we're kind of gunning for. And then we can accept the alternative hypothesis. Again, we have not proven the alternative hypothesis is true. There is still some probability of different types of error. We're going to learn about type 1 error and type 2 error and things like that. That's like the whole business of false positive and false negative and all that stuff. We'll get there. But if we are going to be rejecting that null hypothesis, we're going to accept the alternative hypothesis, and we're going to say we believe that HA is true to some confidence level. So what we're going to need to do, the task that's in front of us here, is to develop a statistic. It's a statistic. It's a number that's going to come to us based on the data that we collected, and it's going to be giving us a sense as to how likely or unlikely that null hypothesis H0 is. If the probability that the H0 is true is not very high, I mean we're talking like 1% or something like that, that doesn't prove that it's false, but we can reject it at some confidence level. We have some confidence that we are not making an error when we are rejecting that null hypothesis. So for example, we're going to be continuing to look at this example of the Creighton students and the UNO students. We're going to do other examples about like wind power and solar power and so on. But we're going to try to come up with what could we do with the heights of the 10 Creighton students and the heights of the 10 UNO students, excuse me, that would give us a statistic that would then give us a way to look at this and say, I see, I could do, H0 has this probability of happening, that's not very likely. Or H0 has this probability of happening and that's not bad at all. It's actually quite likely that H0 is happening. That's where we're aiming for. Those are going to be our inferential statistics. All right, take a little break. Let me know if you have any questions and then move on to the next video. This has been Dr. John Schrage.